Welcome back to Engineering Systems. So today, we are going to get into something really foundational, the CAP Theorem. Now, you've probably heard of it, but trust me, getting a proper handle on this idea, it's one of those things that just quietly rearranges how you think about distributed systems forever.
So here's how we're going to break it down. First, why do we even need this? Then we'll get super precise with the definitions of C, A, and P. After that, we'll look at the big inevitable choice you have to make, compare the two ways you can go, and finally, bring it all back to how this stuff actually works in the wild.
All right, let's get right into it. To really get why the CAP theorem is such a big deal, we have to start with the problem it's trying to solve. Think about a single database on a single computer. Life is beautiful, right? You've got one disk, one chunk of memory, and that means you have one single undeniable truth. Every read sees the absolute latest right. No debates, no weirdness.
But then, you get successful. You need to scale up. You need more speed. You want to be able to survive a crash. Maybe your users are all over the planet. So what do? You copy that database onto a bunch of different machines. And just like that, congratulations. You've just stepped into the world of distributed systems.
And this is where the trouble begins. Because as soon as you do that, you have to pay a tax that nature charges every single distributed system. The network is just not reliable. See, CAP isn't some rule we invented for fun. It's basically a law of physics. Messages get dropped, they show up late, they come out of order. It's a mess out there. Okay, so with that problem in mind, let's get our definition straight. Because honestly, this is the part a lot of people get kind of fuzzy on, and for this to make sense, you have to be super precise. So, a little bit of history. This whole thing started as a conjecture from Eric Brewer back in 2000, and then it was formally proven a couple of years later. And a key thing to remember here is that this isn't just a database thing. Nope. It applies to any distributed system where you're sharing some kind of state. All right, first up, C, consistency. And we need to be really clear here. We're talking about strong consistency, linearizability, if you want the fancy term. It means that to the outside world, your entire system acts like there's only one copy of the data. If I write x equals 5, every single read after that write has to see 5, period. No excuses, no, well, maybe it'll update soon. Next, A for availability. Now this is all about being responsive. It's about liveness, not correctness. It just means that if you send a request to a node that isn't crashed, you will get a response. You're not going to be left hanging forever. Now that response might be stale, it might be old data, but the system guarantees it'll answer with something.
And last but not least, P for partition tolerance. And here's the thing about P. It's not a choice. You don't get to opt out. A network partition just means some of your servers can't talk to some of your other servers. A router fails, a cable gets cut. This stuff is just a fact of life in distributed systems. It's going to happen.
Okay, so here it is. This is the absolute heart of the theorem. What happens when P, the network partition, actually happens? Because it will. This is where the system is forced to make a really tough choice. And the core of the CAP theorem is this. When a partition happens, you cannot have both consistency and availability. It's impossible. You have to pick one. You are forced to sacrifice one to keep the other. Let's make this super concrete. Imagine you've got two nodes, A and B, and poof, the network connection between them is gone. They can't talk. Now, a user writes a new value, let's say x equals 5, to node A. And at the same time, another user tries to read the value of x from node B. So, what should node B do?
Well, it only has two options, and there is no magic third choice. Option 1, it can choose consistency. It can say, I can't reach my partner, so I have no idea if I have the latest data. I refuse to answer. It sacrifices availability to guarantee it's not wrong. Option 2, it can choose availability. It says, sure, here's the last value I saw, even if that value is totally stale. It sacrifices consistency to stay online. That's it. That is the trade-off.
So this choice, this fork in the road, leads to two main families of distributed systems. We call them CP systems, which choose consistency over availability, and AP systems, which do the opposite. And you can really think of them as having two totally different philosophies. A CP system's motto is basically, better to say nothing at all than to lie. Correctness is king. An AP system, on the other hand, is more like, just give them an answer now, we'll sort out the details later. Uptime is everything. And you can see some classic examples of each here. So let's walk through what happens in a CP system, like a traditional database. A partition hits. A follower node suddenly can't reach its leader. What does it do? it immediately puts the brakes on. It goes into a safe mode and stops accepting any writes, maybe even reads, because it can't guarantee consistency. The result? That part of the system is now unavailable, but the data is guaranteed to be 100% correct.
Now let's flip it and look at an AP system like a Cassandra or DynamoDB. The same partition happens. But what do the nodes do? They just keep on chugging along. Both sides of the partition keep accepting new writes, operating completely independently. They stay always on. The upside is the system is available. But the downside? Well, now you have two different versions of the truth. The data has diverged, and you're going to have a headache resolving those conflicts once the network comes back.
Okay, theory is great, but let's talk about how this all plays out in the real world, and maybe bust a few common myths while we're at it.
Yeah, there are a few misconceptions that pop up all the time. The biggest one is that you pick 2 out of 3 for your system forever. That's not really it. The reality is you choose between C and A specifically during the time a partition is happening. Another big one is about eventual consistency. That's not some weird third option that breaks CAP. No, it's actually the AP strategy for how to clean up and get back to a consistent state after the partition is over.
And, our thinking has moved beyond just CAP. There's a fantastic extension called PACELC. It basically says, fine, when there's a partition, you choose between A and C. But what about when things are fine? Else, you have another trade-off between latency and consistency. Think about it. If you want strong consistency across data centers in New York and Tokyo, you have to wait for the message to travel across the planet and back for every single write. That adds latency. So even when the network is healthy, there's no free lunch.
So really, here's the best way to think about it. The CAP theorem is a forcing function. It's a stress test that forces you to answer a very fundamental, very honest question about your system design. When the network inevitably breaks, and it will, what lie are you willing to tell? Because you have to tell one. Are you going to lie about your availability and say, sorry, try again later? Or are you going to lie about the data's truthfulness and say, here's an answer, but it might not be the latest?
And that's the choice. It's not about being negative, it's about being a pragmatic, honest engineer. And that's really the core of the CAP theorem. Hey, thank you so much for watching this deep dive on engineering systems. If this explainer helped clear things up for you, it would be awesome if you hit that like button and subscribed. And seriously, I want to know what you want to see next, so drop a comment below with any topics you want me to tackle.